This recording is protected by copyright. No part may be reproduced without the prior permission of the University of South Australia.
Have a look what it does. See, it just splits off the surface layer, the finished layer of concrete, and that one very quickly moved down to the coarse aggregates. So it can be a significant problem. What I'm doing in showing you this today is so you can recognise it, because people will often ring you up over the phone. You ask them a few questions, and you say, look, can you scrape up a little bit of the concrete? Scrape it off really easily with your car keys? Oh yes, they'll say. Straight away you've got in mind that this is the most probable problem. So it's all about salt hydration pressures. As I said, when the saline solution gets to this surface of evaporation, the water leaves the solution as water vapour, but it leaves behind the solute, namely the salts. They sit in these little near surface pore spaces, and they will change their volume, that is the size of the salts will increase and decrease relative to them being able to absorb water of hydration molecules from the atmosphere or from rainfall, wetting and drying cycles, sprinklers splashing against walls, raining 1 minute, sunny the next, like this sort of weather we're having now is very prone to this sort of thing. So the explanation here is that N20 concrete's got a tensile strength of around 4.5 MPa or slightly less than that. And the salt crystals being hygroscopic, that is the capacity to absorb moisture from the atmosphere, and in a lot of cases deliquescent, that is they can liquefy. It's like putting a peppermint on your bedpost, on your bedside table, get up in the morning and the peppermint's all sticky because it's deliquescent, it's pulled moisture from the atmosphere. And these salts undergo this anhydrous to their hydrated phase change, and that generates significant surface pressures well in excess of 4.5 MPa. That's why we start losing the concrete surface, losing the brick surface, or the cement mortar starts falling to bits that we bond our bricks and blocks together with. Here's a table that just shows you the incredible increase in volume of a little salt crystal sitting in a little pore space in the near right at the evaporative surface of concrete or brick or mortar. And have a look at sodium carbonate. 374% increase in its volume. I mean, it's just going to outgrow. And here's the sodium sulphate. I think I told you 317 before, but it's 315 on this table. And you see, that's the anhydrous salt, and here's the hydrated salt. And it takes on 10 water molecules and 10 water molecules there, and even only 2 water molecules there, calcium chloride. But it's still a 241% increase in volume. So you have no hope of stopping this from happening while all the conditions are conducive to salt jam. Salts plus moisture plus a permeable medium for the saline solution to pass through, and then of course you must have that evaporative surface. And this is how the evaporative surface gets attacked, because these salts are left behind. Here's sodium sulphate, which is in its anhydrous state. It's called phenidite, Na2SO4, and then when it takes on its 10 water molecules, it becomes mirabolite. And where does this happen? It happens between 15 and 25 degrees centigrade, when the temperature's that, and relative humidity of the atmosphere around about 62 to 68% or something. And we've probably got that 3 or 4 times today, or the current sort of weather we're having. And so very easy for that salt to attack a salt dam in the state of South Australia, because our weather conditions are very, very